Hello, everyone. Thanks for joining me today. My name is Valentin. I'm a field engineer. I work at Unity, and I help studios make their games better. So here are my contacts. Just don't forget to follow me on Twitter. So today I'm going to talk about the specifics of memory management on iOS. And this is a rather hard and confusing topic. But this session will make everything much more confusing, but more structured. So get ready. So most of the information in this session is applicable to other platforms, but it has to be researched and tested, because I only tested this on iOS. I understand that this is a rather hard topic and is very technical. So I prepared a document which contains much more detailed information. And I will share the link to this document at the end of the session. So there's no need to take a picture of every slide. So say you have a game. You build it on an iOS device, be it an iPad or iPhone, and you want to know how close to the memory limit you are. So the question is, how much memory does my game take? I hope that you all know these tools. So there are a few really good tools from Apple and from Unity, which can help you see everything, all information about your game. I will not go into detail. I will not go into details about how to use these tools. For this, I recommend you to watch other talks from Unite on YouTube, for example, or talks from WWDC conference. So the question is, which value is real? So when you ask the question, how much memory does my game take? The thing is that this question is ambiguous, because we don't know what kind of memory you are talking about. And it is critical to understand what kind of memory we are talking about. And I want you to be familiar with like different kinds of memory on iOS devices. And on the next few slides, I will present an overview of different kinds of memory. And I really hope that like by the end of this presentation, you will have a much better understanding of how memory management works on iOS devices. So first, we have physical memory. This is the total memory on chip you have on your iPhone or iPad. For example, you might have 512 megabytes or 1 gigabyte. But the thing is that you cannot have more because it's physical hardware on chip. So each running application consumes a part of this physical memory. But the thing is that in modern operating systems like iOS, applications never work with physical memory directly. Instead, they use so-called virtual memory. So when an application starts, operating system gives it a private address space or virtual address space. And it's called virtual because it is not necessarily aligned with the physical address space of the machine. This virtual address space or virtual memory is divided into small chunks of memory, which are called pages. And each page is 4 kilobytes on older devices and 16 kilobytes on new devices. So when an application requests a memory address in virtual memory, The operating system uses a page table to map this address into the physical address. Slight issue with this. Okay. So I hope this is clear. This is basically the private address space of the application. So an application can allocate a block of memory from virtual space, but it can not really use it for anything. This is called reserve. The application has to write to this memory to actually make the operating system to allocate some part of physical memory for this block of virtual memory. This is called to commit. And this reserve and commit are words we will see at some point at the presentation, so take note of that. So resident memory is a total amount of physical memory used by the application at any moment. And you can see I highlighted currently the resident memory. Resident memory is divided into what is called clean and dirty memory. Clean memory is all memory pages in resident memory which iOS can safely unload to free space and reload from disk later because they're read-only. Dirty memory is pretty much everything else. It is a resident memory which was modified at some point, and the operating system just cannot unload it. The cool thing is that since clean memory is read-only, applications can share parts of it. So, for example, they can share system frameworks and libraries. Memory allocated for the following things is considered clean. These are applications binaries, system frameworks, libraries, memory mapped files, static code segments, and stuff like that. So, for example, here I outlined that the binaries of the application of your actual game go to this clean segment of memory. Graphics memory. Usually, for example, on desktops, graphics memory is a separate hardware on a GPU. Like you have like a CPU, random access memory for CPU and GPU. They're totally separate things. On iOS, iOS uses so-called unified memory architecture. That means that GPU and CPU share the same physical memory. So graphics driver allocates memory for its needs, for textures, meshes, shaders, and stuff like that in virtual memory. And you can see how it looks here. So it's a part of your application virtual memory. And most of it resident and dirty. There's a region of virtual memory called malloc heap, and it is where application can allocate memory using malloc and other C functions. So this is basically where Unity allocates memory for all its needs. Unfortunately, Apple doesn't publish the actual size of this region. But from the test, it seems that the size is around twice the size of physical memory. So if you have like 1 gigabyte of physical memory, the malloc heap will be 2 gigabytes. So the next one is swapped compressed memory. I hope that like this image is kind of clear and doesn't make everything more confusing. So in like desktop operating systems like Windows, you have this thing called a page file on disk. This is where Windows dumps rarely used virtual memory pages to free physical memory. So iOS doesn't have that, but instead iOS can compress memory and move it into another region of physical memory. So in other words, like swapped compressed memory is a part of application's dirty memory, but compressed and stored like, somewhere else. So you can see here that there's a dirty memory, which is in reserved memory right now, plus the compressed memory. The algorithm used by the OS to do this, to compress and to move pages, is not known. But from the test, we see that iOS tries aggressively doing this and compress as much memory as it can. So we get to more Unity-related stuff. Unity is a C++ engine with a .NET virtual machine. And it allocates memory for all its resources in what is called native memory. So native memory is a part of malloc heap used for all Unity's allocations. So, for example, when you create an instance of texture 2D class, all its actual data, the texture data, will be allocated into this block of memory, native memory. And it will be exposed to C# scripting as a lightweight wrapper you can work with in your C# code. It's worth mentioning native plugins. For example, when you use when your application uses a native plugin, it allocates its own memory. It allocates it in malloc heap, but Unity doesn't see it. And I mean that Unity, as a Unity profiler, doesn't see it. And the binaries part are still in the clean memory, so you can see are outlined there. A part of native memory allocated specifically for the .NET virtual machine needs is called mono heap. It contains all managed objects and is maintained by a garbage collector. So basically, when you create an object in C#, it goes there. So one point though, a picture of mono heap being a contiguous block of memory is not true. So the top square is not how it looks in reality. Mono heap is allocated in blocks of some size to hold C# objects of like similar size. So you can see the blocks on the bottom picture. So a block can be allocated, committed, as you remember the terms, but not used. So that means that the block still uses physical memory, but it's kind of not a part of mono heap which you can use. So if after several garbage collection passes, there are still blocks which are allocated but not used, they are returned back to the system or decommitted, thus freeing physical memory. So for iOS, the specific number is 8. So if you call gc collect 8 times, we'll see that. But the issue with the blocks is that they're usually fragmented. So as you can see here, like the green ones are actual C# objects in memory. So a block can be rather large, but contain just a few C# objects. And this means that it's not free, it cannot be removed. And unfortunately, this is the usual case in real-world scenarios. So iOS is a multitasking operating system. Several applications can run on it and share memory, each one with its own virtual memory space mapped to physical memory. when the amount of free physical memory is low, iOS starts trying to reduce memory pressure. And it does it the following way. So first, it tries to remove clean memory pages, because they can be reloaded from disk because they're read-only. If the current active application takes too much dirty memory, iOS sends memory warnings to the application. If the application, after several memory warnings, still consumes significant amount of dirty memory, iOS kills the application. So unfortunately, Apple, once again, doesn't publish the exact details of the algorithm. So sometimes we can see that one application can allocate this amount of memory and get killed, but the next run it allocates 20% more and survives. So you probably already guessed what advice I can give you. It's minimize the size of dirty memory, because dirty memory cannot be unloaded by the operating system. So you can use these tools to measure the size of dirty memory and see if it grows over time. And you should think how to reduce the number of objects which contribute to dirty memory. Another interesting point here is that some of the dirty memory can be compressed, as we already discussed, and some data can compress better, some data can compress worse. So we cannot really know in advance this. There are reasonable memory limits we've seen in the wild. There are like this. But the thing is that even if you use less memory, less dirty memory, your application can still get terminated by the operating system. But if you go further, these limits, your chance of being evicted from the device is much, much larger. So let's see what values we can get from the tools, and try to see what kinds of memory they are showing. As already mentioned, Apple provides really great tools, and Unity provides tools which are easier, but also very good, and they all show slightly different things. So the first one is probably the easiest. It comes with Unity, it's Unity Profiler. And it shows a few interesting things. So I tried to highlight them. So the first one is mono used. This is the size of mono heap. So basically on the screenshots, it is the sum of pink and green blocks. Next, mono total, the total size of committed blocks for the mono heap. This is the size of all colored blocks there. GFX driver. So right now for iOS running with a Metal API, this shows only the sum of 2D textures. From what I know, the most recent version of Unity in development is going to show much more data in this GFX driver value, including also other textures, meshes, and different buffers used on GPU. And another one is fmod. This is a memory taken by fmod audio engine. And so that's probably it. The thing is that this particular view hasn't been updated in a while, and it seriously needs an overhaul. So, for example, like total value, it doesn't include really big parts of the application size in memory, like game binaries, libraries, and frameworks, and as I said, native plugins. And the GFX driver doesn't show all the GPU memory. So the profiler only kind of sees what Unity itself sees. But this is pretty much the only tool which shows you the actual size of mono heap. So Unity Profiler has another view, which is called Detailed View. And the greatest thing about this is it shows the actual named objects which are in the in native memory. Because all other tools, especially from Apple, they show the blocks of memory when they were allocated, but they don't show basically why and what's inside of them. And here you can see the actual named objects. So on the first screen, on the top, we see that there are many large sounds in the application. So these probably don't have right compression settings. On the bottom, we see a few textures with identical names. Usually it indicates that these textures are duplicated. So basically it's the same texture with the same data, but which is in memory twice for whatever reason. Next one is called like this, Memory Profiler. And this is a tool based on Memory API from Unity 5.3, and it's available on Bitbucket, so it's not shipped with the Unity. So it looks like this. It basically shows a combination of assets in virtual memory, assets on GPU, and the managed objects in mono heap. It is super useful. If you haven't tried it, I really recommend to use it. You can see that the largest green block is our sounds. There are a bunch of textures, the pink blocks. So it also shows which objects reference the objects which are in memory. So you can figure out why a specific texture, for example, is not unloaded. And it's really easy to see relative sizes. So you can see that like, sounds take a huge amount of memory, and it's like screaming at you. Oh, by the way, there's this link where you can get it. So you can zoom in with this view and see smaller objects. For example, here, this is zoomed in view where I highlighted an array of strings. This is a managed object, and the tool also shows you the content of this array of strings. This is kind of cool. The next one is also based on this same memory API, but it shows slightly different things. It is available on GitHub. You can find it here. And this tool was made by our support team to visualize Heap and allocations. So as you can see, this tool can show you the actual state of the mono heap. So we can see here that there are 3 blocks, each with a highlighted size. And the total is 64 kilobytes, which is the same as we've seen in Memory Profiler, like 0.6 megabytes. But this tool also shows the total sum of all managed objects in mono heap. And you can see that it's actually a much lower number. It's 86 kilobytes. Also note the fragmentation of the heap. Like the objects are all over the place. So when you run your game from Xcode, you will get a number of gauges in the Xcode debug navigator view. And one of them shows how your memory is doing, how your device is doing memory-wise. So unfortunately, it's not totally known what this bar shows exactly. But it seems that the value is usually around the sum of dirty memory and swapped compressed memory. So you should use this value just to figure out if your application is doing okay memory-wise, because usually it seems when the value goes into the yellow zone, it's soon killed by the operating system. And of course, for detailed profiling, you should use instruments, and we'll get to that on the next slide. So Apple gives us other cool tools, and the best one is called VM Tracker Instrument. It basically shows everything about your game, about your application. So the main window looks like this. This tool is rather complicated and I would say hard to master. So I recommend you to watch videos from a WWDC conference where they explain how to use VM Tracker and other instruments. You can see they're virtual, swapped, dirty, resident. And we already know what these are. So let's look closer. So I highlighted the things I'm going to talk about, so you can keep up with this. So let's see. Virtual, A, total memory consumption. The app has allocated 1 gigabyte of virtual memory. It has committed 351 megabytes, which is dirty plus, no, which is resident plus swapped. So 186 plus 165. C, it has swapped 165 megabytes. So D, now it is 186 megabytes of physical memory or resident memory. So this is the amount of memory your application actually consumes on device. And 118 megabytes of which is dirty. These are clean memory. So highlighted with blue, you can see the binaries. And you can see that they take resident memory, but they don't consume dirty memory. So you can see the values of 0 there in the column. So this means that they're clean. And specifically, this memory can be unloaded when the application needs more free space, basically. So what else can we see? VM Tracker shows a bunch of groups and how much they contribute to virtual memory and dirty memory. So the basic groups are the following. All allocations, all dirty allocations. This is all allocations contributing to dirty memory. Allocate, this is a graphics driver. So I highlighted it here. So we can see how much memory is allocated by our GPU resources, like textures, shaders, and meshes. The next one is VM Allocate on the bottom. And this is actually mono heap plus some other mono allocations. And we can see, like we can see here that it's like 1.5 megabytes. And the actual mono heap is, I think it was like, okay, I don't remember where I captured it, like about 0.5 megabyte. So the next one is malloc underscore something. This is a malloc heap. The next one is a text and link edit. These are application lib binaries and application binaries and library binaries and frameworks. These are read-only and usually clean. Data. This is writable, executable, and static data, which can be clean or dirty. And you will see a lot of other small things, like performance tool data, for example. This is the overhead of instruments themselves. To better understand how this works and what this tool shows, we advise to use it with your game, with your application. Just actually try to profile your game with this. It's rather cool to explore the values. Unfortunately, VM Tracker doesn't report what memory was allocated for and when. It only shows allocated blocks. There's another useful instrument called Allocations, which shows actual allocations within a time period, and all allocations are timed, and it also shows the call stack where the allocations came from, like so. So here we can see an example. This is a loading thread, loads a scene, which in turn loads a bunch of sounds. And we've seen this a couple of times already. The sounds take like 100 megabytes. So you can see like loading thread, scene is loading, fmod initializes, Unity allocates memory. And you see how much this process takes. This is all virtual memory, by the way. Another two examples. So the first one is Unity loading asset bundles. And you can see I highlighted there the code which allocates memory for I/O operations. And the bottom one is a bit tricky. So with this tool, you can see what is actually going on under the hood in IL2CPP virtual machine. So here we can see how an instance of a game manager class is being created. And since it's created for the first time, IL2CPP has to load some metadata for it. And you can see the allocation. So this tool kind of partially answers the question, where does my memory go? And I want to show you an example. It is a bit artificial example, but it simulates the usual task of loading and parsing JSON file, which a lot of people do. So it consists of 3 steps. Load and parse a 350 kilobytes JSON file, call GC collect once, call GC collect 8 times. So let's see. So first, actually step 0, initial state before we load anything. We need to check this out to compare. So here I pasted screenshots from different tools which show slightly different details about the same thing, about mono heap. So the top one, Unity Profiler, it shows that it reserved or committed half a megabyte of memory for mono heap needs. But the actual size of mono heap is 364 kilobytes. We see the same in VM Tracker, which shows 2 blocks of memory allocated for this precise reason for the mono heap. You can see them there highlighted. And allocations show more data about this. So you can see that those 2 blocks of memory, those 2 allocations, are shown on the bottom by this tool. So there are a few important things. The first one is notice the category. This is the name of the category where where Unity allocates memory for mono heap. And another one is that several allocations can be in one memory block. So you can see in allocations there are first 3 allocations, which all go to the first memory block in a VM tracker. Allocations instrument can show much more data, and the coolest thing that it shows the actual call stack of an allocation. So we can click on each of them and see what code made the allocation. And from this, we kind of can guess why and what the memory is going to be used for. So the first 4 allocations, the call stack is on the bottom. This is IL2CPP virtual machine initializing. And you can actually see if you can read this. It's IL2CPP VM runtime init. But the last allocation is done when creating a managed object. This means that the monoheap had to expand at this point to allocate some memory for this managed object. You can see on a screenshot on the right from you the call stack of this managed object being created. The object is called culture info. So you can see that the constructor of culture info caused some monoheap to expand. The same thing viewed with other tools. Unity Profiler shows like 364 kilobytes, as we've seen already. But that other tool, which shows more info about monoheap, shows us 2 blocks, which we already know that there are 2 blocks. And it shows the actual size of all the objects in these blocks. It's like 58 kilobytes. So once again, notice the fragmentation. So now we know the initial state. We can compare with the state of the application after we parsed the JSON file. So looking through Unity Profiler, first, notice that this is a rather expensive operation. So it took half a second to just load and parse the JSON. Total memory allocation during this process was 5.6 megabytes, which is shown by the profiler. But notice that monoheap has not expanded that much. And this is because garbage collector has run a few times during this process to free some amount of memory. So from here, we can see that current size of monoheap is 3.3 megabytes. Current committed size of monoheap is 4 megabytes. Let's look at this with other tools. So in Allocations instrument, I selected specifically that part of the timeline where the parsing took place. So these are only new allocations. And we can see that looking at Allocations instrument and the VM tracker, we can actually map the allocations from one tool to another. And I tried to highlight them with colored numbers. So you can see that 1 on the top maps to 1 on the bottom, but 3 and 2 are actually in one memory block, so they're combined. So here we also see that the whole VM allocate group takes 4.7 megabytes of virtual memory. And from the data we've seen earlier, we know that the monoheap size is around 4 megabytes, which we have already seen with other tools. Also notice that all monoheap is dirty. So there's one interesting thing. if we look at these allocations, we can notice that each one is kind of twice bigger than the previous one. And this is kind of interesting. And we can click each allocation and see the call stack, which I pasted there. So we can see that these allocations are caused by string builder class expanding. So while parsing this JavaScript and or JSON, while parsing this JSON, which is like a huge wall of text, a string builder is used, and to allocate more data for its needs, it expands but allocates twice more memory than the previous allocation. And this tool is rather cool, and you can see all this with your own eyes. So here we see pretty much the same, the state of monoheap. So once again, committed size 4 megabytes, heap size 3.3 megabytes. And if you look at the top, there's a number of total size of currently created C# objects, and it is 1 megabyte. So after we parsed JSON, a lot of monoheap is just not used; it's just free. And also notice the fragmentation. So let's see what happens when we call gc collect. So first thing we see is that mono heap size has decreased, as reported by Unity profiler. So this is highlighted in a yellow. This is 2 megabytes. But the thing is that actual allocated and committed memory has not changed. This is shown by VM tracker, which didn't change at all. And also this is shown by mono total in Unity profiler. So, but notice that some memory pages from monoheap are now compressed, because iOS aggressively tries to compress all the things to free memory. So this kind of means that though we ran garbage collection and free some monoheap space, the actual physical memory which is taken by the monoheap has not changed. And iOS actually cares about physical memory, or in this case, dirty memory. So, and the last step is we check what's going on if we call gc collect 8 times in a row. First of all, you can see that it's a rather expensive operation to call gc collect a few times a frame. So after doing this, Unity profiler actually shows that mono reserved has decreased, shows 2.4 megabytes. And if we take allocations and the VM tracker instrument, we can see the following. So on the top, once again, I selected precisely the region of time where we called gc collect 8 times. And there I see these 2 items, and they say that 2 allocations were actually decommitted from memory. So one of these is 1 megabyte and another is half a megabyte. And I also pasted the part of the call stack for this. So it starts at gc collect, and goes and basically decommits the memory, which is good. And we also can see the effect in VM tracker. So look at the bottom 2 rows. So you can see that these allocated block, they are still allocated in virtual memory, So they still consume virtual memory. Remember the private address space. But they contribute 0 bytes to resident and dirty memory. So this means that this part of virtual memory isn't actually mapped to any physical memory. So I hope this example simplified something for you. And you know better how to use the tools right now. And you know how to make sense of the data that the tools provide. So as I told you at the beginning, here's a much more detailed document. And the document itself contains a link to the slides if you want to look at the slides again. And I probably have questions right now. Okay. So, oops, something happened. So there are no questions. So either it was super complicated and nobody understood anything, or it was super basic and everyone knows everything. But after you read the document, it's on Google Docs. So you can write comments right there and ask your questions there. So thank you for coming and have a nice day.